Okay, so our first sort of flipped lecture here for our remote learning period is going to be in a learning unit on Chapter 19 on ionic equilibria and aqueous systems. So today we're going to talk about qualitative and quantitative aspects of buffers, pKa and pH and their relationship in the Henderson-Hasselbalch equation. Conceptually, we'll talk about how you actually make buffers. And again, buffers are made up of weak acids and its conjugate base. We'll talk about concepts of buffer capacity and strength. And then from a skills to practice standpoint, we'll actually talk about how you calculate pH changes when you have addition of either acid or base to a buffer. Lots and lots of homework problems to practice these concepts. Please do not feel like you need to get all of these problems done at once. Use them as an opportunity to practice things as you sort of go through this chapter. So again, just a reminder of where we've been as we move into our third chapter here in Chapter 19 on equilibria. We introduced equilibria in Chapter 17, and that's when we first learned about Ks, and we learned about an equilibrium constant, Kc and Kp, the concepts of Q versus K. And then in Chapter 18, we had our first specific application of equilibria, talking about acids and bases. So we learned about Kas, Kbs, and then Kw as the specific equilibrium constant for water dissociation. So a lot of what we're going to see in this chapter is going to be the same. We're talking about systems that are at equilibrium. Equilibrium constants are written as products over reactants. So again, what's going to become different here is the kind of chemistry that we're talking about, and specifically the complexity of the problems that we'll need to solve. So this chapter is really the culmination of concepts that were introduced in Chapter 17, built on and applied on with Chapter 18 in acids and bases, and now really are kind of integrated here in this last chapter. So again, we're going here to talk about two main concepts in this learning unit. We're going to talk about acid-base chemistry, but specifically when we mix acids and bases together, specific acids and bases, we can get buffers. And these are really important because you want to know how you maintain blood pH. You do it through buffering by carbonate and phosphate systems. And then we'll actually tell you that we lied you a little bit in Gen Chem 1 when we told you that some salts were not soluble, and we had that table in Chapter 4 that said, hey, these salts are not soluble. We're going to reconcile that and say, you know what? Yep, they were soluble. They were slightly soluble, and we can use an equilibrium to actually discuss just how soluble they were. So a little bit of terminology here and then some applications of how we'll use these. No specific problems or homework problems with this, but again, you will see some examples of things like this on your next test. So pH is a property of the environment, and it talks about and reflects the concentration of H+ that you might have in solution. So the more acidic a solution is, the lower the pH is, and the higher the H+ concentration is. So those are concepts we learned about in our last chapter, Chapter 18. When we talk about pKa, you can think about pKa as being a property of a molecule. It really reflects how easily a proton is removed from a molecule. That is, how tightly does that proton held onto with that molecule. So again, there is a relationship between pH and pKa, and you can think of pKa as being the pH you need to be at in order for half of your molecules to be deprotonated. So let me say this a couple times in a couple of different ways. If you have a molecule, for example, that has a very high pKa, that means you have to be at a very high pH, a very basic situation, in order to get that molecule to let go of its proton. So that must mean that molecule is a relatively weak acid because it's holding on to its proton tightly. So again, if you need to rewind and replay this segment a couple of times to get this into your brain, please do so. But we can think again about the relationship of pH and pKa to determine protonation state. So protonation state really refers to, does your molecule have its proton, and we'd say it's protonated, or has it lost its proton and it's deprotonated? And you need to know information about both the environment and the propensity of this molecule to hold onto its proton in order to answer that question. So if we think about this just from a very general standpoint, we can show an acid here as a molecule HA. So that ability to lose its proton is related to the acidity. The stronger that acid is, the weaker it's holding on to its protons. So weak acids hold on to their protons more tightly because they live in this space. Strong acids live more in this space, so they are not holding on to their protons tightly. If we think about this another way, as we increase the pH of our solution, we're going to be increasing the hydroxide concentration. Hydroxide is going to be able to react with that water or that proton and make water, and it's going to shift the equilibrium to the right. So again, if we want to get a molecule to let go of its proton, if we increase the concentration of hydroxide, it can pull the protons off and it can shift this equilibrium to the right. So again, increasing hydroxide concentration happens when we increase pH, and so that's going to happen when we have a weak acid, something that's holding onto its proton more tightly. Okay, so let me put this in a practical context and the kinds of things you're likely to see on an exam question. I'm going to ask you for a certain molecule, is the molecule protonated or deprotonated at a specific pH? So all you need to be able to do is compare pH and pKa and ask the question, which number is bigger? If pH is bigger, that means the environment wins. It's going to take the proton from the molecule, and the molecule will be deprotonated. And this is all written down in your How Do I Know How To sheet. But if pH is greater than pKa, that means the environment wins because pKa or pH is a property of the environment. If the environment wins, that means the molecule is deprotonated. On the other hand, if pH is less than pKa, if pKa is a bigger number than pH, that means that the molecule wins. The molecule gets to hold on to its proton, and we'd say that that molecule is still protonated. So a very important skill for you to be able to know is how to determine the protonation state of any given species. You cannot determine the protonation state unless you know both the pH and the pKa. And then at the end of the day, it's really just a numbers game. Tell me who's the bigger number, and that wins. If the environment wins, then the molecule's deprotonated. If the molecule wins, then the molecule stays protonated. Okay, so that's pH, pKa, and protonation state. But as we're going to see here in just a couple of slides, we can relate those mathematically with an equation. All right, other things to think about here. If we're going to make a buffer, okay, and this is where this chapter becomes a little bit different from things that we talked about in chapter 18. When we make a buffer, we really are going to have a solution prepared from a conjugate acid-base pair. Okay, so here's two examples of conjugate acid-base pairs. So we could have a weak acid mixed with its conjugate base. So for example, if we've got acetic acid, if we just let acetic acid dissociate, we would have mostly acetic acid in its protonated form and just a teeny tiny bit of the conjugate base form. That's what it means by definition to be a weak acid. When we make a buffer, we're actually going to add the acid to solution, but also add its conjugate base, usually as a salt. And when we have both of these in solution, by definition, we have a buffer. So you can make a buffer by mixing a weak acid and its conjugate base. It's not just mixing an acid and a base together. It's mixing a weak acid and its conjugate base. Or you could mix a weak base and its conjugate acid. So an example of that here would be if we were to mix ammonia, for example, and then again, the equilibrium that we would think of would be this guy. But the idea is that we are going to have a weak base and its conjugate acid that we both add to solution. We're not saying that this equilibrium happens and creates both of these by only adding one component. We're really going to be adding both of these components to the same solution and generating a buffer. Okay, so that's qualitatively how you make a buffer, is you need to mix together an acid, a weak acid, and its conjugate base, or a weak base and its conjugate acid. So likely questions that you're going to see in the exam would be, which one of these represents the best buffer? Now, for example, if I were to mix this weak acid and this weak base, they are not going to make a buffer because they are not a conjugate acid-base pair. They're not matched. They need to be matched together here. Okay, so relating again pH and pKa, we can have a magic equation that we're going to see a lot in this chapter. So I want you to know how to use it. This is the Henderson-Hasselbalch equation, and there's essentially 4 variables that we have here. pH of the environment, pKa of your molecule, whatever that molecule is, its concentration, and then the concentration of that molecule's conjugate base. So 4 variables, and we're generally going to be solving for one of these variables as an unknown. So this is going to be a really important equation that we'll see used in 2 ways. We're often going to see it used to calculate the pH. So this is going to be our unknown when we know we have a buffer solution. So we have a conjugate base and a weak acid. And since we know what the weak acid is, we can look up its pKa on a table. And so we'll know 3 variables here, and then we'll be able to calculate our unknown, which is pH. So this is going to be the predominant way that we will use this equation. But we will see a couple of examples if you wanted to make a buffer. It allows you to figure out what are these concentrations that you'd need to have so you could actually go into the lab and make that buffer. Okay, so just a little bit to think about what happens with buffers and when we add acid or base either to water or to buffer. So let's focus just on this top panel here for a second. What we can see here is a pH meter that's recording the pH of, this is again going to be an unbuffered solution, essentially pure water that's slightly on the acid side. And when we add more acid to it, because we're producing hydronium or H+ ions in water, we see a lowering of pH. So if all we added was 1 milliliter of 1 molar HCl, we drop the pH by 3 pH units. That's a lot. When we add a base to pure water, because we're adding hydroxide ions directly to water, again adding 1 milliliter of 1 molar sodium hydroxide, in this case, we increase the pH substantially. And part of what's happening there is because we are adding these species directly to solution, we are changing their concentration. And as we know from last chapter, if you change the H+ concentration, you change the pH. If you change the hydroxide concentration, you change the pH. So what then happens when we have a buffered solution? Remember, a buffered solution has a weak acid and a conjugate base. So we're going to kind of treat this as though we were playing like an army men game. And we're going to call these weak acids and conjugate bases soldiers. We're going to say that these guys have the ability to do chemistry with either acid or base that's added so that we lessen or buffer their effect. So again, for example, if we're going to add HCl to solution, we're going to be adding H+ ions. Those H+ ions can do chemistry with our conjugate base. What that's going to happen, or what's going to allow to happen, is we are going to eliminate H+ ions in solution, and so the change that we have on pH is very minimal. Similarly, if we were to add hydroxide ions to solution, hydroxide ions have the ability to react with an acid. We're going to then essentially neutralize those hydroxide ions that are added, so they're going to have a minimal effect on increasing the pH. You will notice that when we add acid, it's not that there's no change, it's just a minimal acidification. When we add base, it's just a minimal increase in pH. And on the next slide, we're going to understand why that is. So again, I want you to think about buffers being pH guardians. Think of this as being like an army that helps kind of buffer or combat the addition of acid or base. So let's kind of focus here over on this left side here. Okay, so again, this is going to be our buffered solution. Remember, buffer has a concentration of weak acid, which we have here, and its conjugate base, which we see here. If we add acid to solution, that acid can react with our conjugate base. That chemistry is shown down here. When we have H3O+, it can do chemistry with the conjugate base and generate the weak acid and then water. This is a one-way reaction, so nothing on the left or on this right side here kind of stays in solution. The only things we have after the chips fall with this chemistry is we've got a little bit of our conjugate base that is lost, a little bit of our weak acid that is gained, and then we generate some water. So if we kind of look at this in terms of, imagine these two guys represent the identity and then the amount of our armies. We've got equal amounts here of both of these armies. We've got an acid army and we've got a base army. When we add more acid to it, we're going to actually do chemistry with our base army and we're going to deplete it a little bit there. So we see that that level goes down a little bit. But since we make a little bit more of our weak acid, this army gets increased, and we can see that there. But importantly, we eliminate any H3O+ from solution, and because we haven't changed the H3O+ concentration significantly, we don't significantly change pH. All right, so that was a lot of information. Let's try doing the same type of analysis if we look at what happens if we add base to solution. So again, when we add a base, and this is a really, really important concept to think about, when we add a base is not going to react with another base. A base is going to react with an acid. So when we have this base that's added to solution, our acid army is now going to neutralize that added base. So that weak acid is going to react with the added base. We're going to generate a little bit more of our base army, sacrificing a little bit of our acid army, but in doing so, we neutralize that addition of base, and so there's minimal change in our pH because we don't have that hydroxide ion in solution. So again, think of your buffers as being pH guardians. These guys are your soldiers. They're going to react with excess or added acid or added base. They'll change their composition a little bit, but we are going to be eliminating any base or acid in solution so that we minimize the change in pH. This is such an important concept. If what I've said there doesn't make sense, I would highly encourage you guys to go back and rewatch this, listen to it, ask me questions, make sure that this makes sense, because conceptually it's important to understand how we make buffers and how they work. So a couple of things to think about with buffer capacity and buffer range, we can relate to what we see with this picture. So remember I told you I want you to think of this representing the identities and then the sizes of our armies that we have here. So the best buffer has equal amounts of its acid and its base armies, and it has large amounts of both of those armies. And that's kind of what you'd expect if you were playing Army Men and this is what was going on. So again, buffer capacity is a measure of the strength of the buffer. And again, that's the ability to maintain pH or maintain minimal pH changes if we've added strong acid or base to solution. And as I mentioned, to have this be effective, we want to have relatively high concentrations. So we want to have large armies. So we want to have the number of soldiers being high. And we want to have relatively equal amounts of both kinds of our armies. We want to have both kinds of soldiers. So again, we want to have relatively large and equal amounts of both of these guys. So how do you do it? A buffer that has the greatest capacity is going to have one where you choose a buffer whose pKa is equal to the pH that you want to be at. So again, another important sort of part 1 skill to this chapter is me giving you a list of different substances and saying, you want to make a pH or a buffer at pH 5. Which acid is going to be the best one to use? You're going to want to pick the one that has a pKa closest to 5. That's going to make the best buffer. Okay. Buffer range is the pH range over which the buffer is effective. So again, if our Army ratio gets greater than a 10-to-1 kind of ratio, the buffering action is going to be poor. We're kind of deficient in one side of our Army. And so we can define the buffer range as not being more than 1 pH unit away from the pKa of the acid. That's just sort of reiterating what we have up here. If pH is equal to pKa, then we are actually within 0 pH units. We are perfect. We are spot on. So you don't want to pick something that's more than 1 unit difference there. Okay, so that's sort of the qualitative stuff to think about buffers. So quick problem here to kind of ask you guys to think about this. I'm going to set up the problem here, and again, what we'll do here is I'll ask you to pause the video and then work through this problem on your own and see if you can get to the answers. So first problem here asks us to look at these molecular scenes here and then ask which buffer has the highest pH. So remember, when we're looking at these little blue guys represent protons that are on an acid. So this guy represents our weak acid, and then this guy represents the conjugate base. We're actually not showing H3O plus molecules here, but what we're really showing is how much this weak acid has dissociated. So again, we've got weak acid, and then we've got its conjugate base. So try to use that information to think about which of these buffers has the highest pH if we're looking at a ratio between a weak acid and its conjugate base. Thinking with the next problem, which one has the greatest buffer capacity? Remember how we defined capacity? Relatively large army with relatively equal kinds of both soldiers, the weak acid and its conjugate base. And then the last question says, if we're going to add a strong amount of, or a small amount, of concentrated acid or strong base, what are we going to want to add if we want to convert sample 1 into sample 2? So if we want to take this solution and make it look like this guy, do we want to add acid or do we want to add base for that? Okay, so I want you to pause the video now and think about those problems. And when you're ready to see the solution, because you've either worked through it on your own, or again, if you're a little bit stuck and aren't quite certain what to do, you can just repress play. But I want you to pause and see if you can work through this problem. Okay, moving on now to the solution for this problem here. I'm going to go through this sort of in steps here. When we think about determining which buffer has the highest pH, again, all of these are going to be the same, so pKa is going to be the same. So if we want to find the highest pH, we basically have to look at this ratio, and we have to ask for this ratio, which has the ratio that's greater than 1. So again, if this number is greater than 1, the log of something greater than 1 is going to be a positive number, so that's going to increase the pH the most. So what we need to do here is look at the number of conjugate base species that we have, the number of weak acid species that we have. And again, looking at this ratio will tell us what we want. Again, if we want something that the pH is going to be equal to the pKa, that's going to have a ratio of 1, meaning we're not adding anything. If we want to increase the pH, we want to have a ratio greater than 1. Decrease the pH, we want to have a ratio less than 1. So we can see here, only solution 4 is going to have a ratio where we have more conjugate base than acid, so that one is going to have the highest pH. Working now through the question, which buffer has the greatest capacity? Again, the greatest capacity means we're going to have the greatest size army. So again, if we look at these 4 solutions and we add up the total number of soldiers that we have in each, we can see that buffer 3 has the greatest army, so that one is going to have the greatest capacity. This last problem here now asks us to think about if we wanted to convert sample 1 into sample 2, what do we want to do? Do we want to add base or acid to do that? Well, again, we need to think about looking at the number of conjugate base or the number of weak acid species that we have. Converting solution 1 to 2 here, we can see that going from 1 to 2, we are going to be decreasing the number of conjugate base species we have and increasing the number of weak acid species that we have. The only way to do that is to add acid. So hopefully those problems made sense. Hopefully it was something you were able to work through on your own. The last problem here is thinking about how we prepare a buffer. Remember when we were talking about the Henderson-Hasselbalch equation here? We said that there's 2 ways that you could use the Henderson-Hasselbalch equation. Most of the time in this chapter we're going to use it to calculate pH, but this is the time we're going to use it to calculate amounts of weak acid and conjugate base that we need to combine together to make a specific buffer. So this problem is telling us that we want to make a buffer that's pH 10, and we're going to add sodium carbonate here and then sodium bicarbonate to make the buffer. So they're already telling us the amount of sodium bicarbonate that we want to have, but we want to know how much sodium carbonate do we need to add so that we're having the correct ratio of those 2 species to have a pH of 10. So again, to set up this problem and give you a little bit of a clue, you want to use the Henderson-Hasselbalch equation that, remember, has 4 unknowns. We know the pH, we know the Ka, so hopefully it's straightforward for you to figure out the pKa, and we know the molarity of the sodium bicarbonate that we want, so we need to figure out the grams of sodium carbonate to add. So again, I'm going to give you some time if you'd like to pause this to work on this. The answer that you're going to want is 15.0 grams of Na2CO3. So again, I encourage you to pause the video right now and see if you can work through this problem on your own. If you need some hints, let's slowly start revealing this problem. We know that we have a buffer that we want to make, so we're going to have a weak acid and a conjugate base. Our weak acid is going to be bicarbonate, and our conjugate base is going to be carbonate. We generate the carbonate from our sodium carbonate salts, and we generate the bicarbonate from our sodium bicarbonate salts. They tell us the concentration that we want to have of this sodium bicarbonate. We know the Ka, so we can get the pKa of our bicarbonate, and we know the pH that we want to be at. So if we think about the Henderson-Hasselbalch equation that we want to use, we basically can solve for the concentration of carbonate that we need. Moving on to reveal a little bit more. Again, here is our Henderson-Hasselbalch equation. They gave us pH, they gave us Ka, which we can take the negative log of to give us pKa. This again is the species that relates the concentration of the conjugate base to the weak acid. And again, we know this species. We know that it's going to be 0.2 molar. So again, walking through what we have here, the pH is given, pKa is indirectly given as Ka. If we want to solve this for this ratio, we essentially are going to take 10 to the both sides, so 10 to the minus 0.3279, 10 to the minus log of the conjugate base of the weak acid equals the conjugate base of the weak acid. And so we can figure out that the conjugate base concentration is 0.0940. Keep in mind, this still doesn't answer the question. We want to know how many grams of sodium carbonate. So take a minute and see if you can figure that out. Pause the video, or again, let it play if you want to see the worked out solution. So knowing that the conjugate base concentration needs to be 0.0940 molar, we can say, well, I know if I want 1.5 liters of that solution, I can use that to tell me how many moles of sodium carbonate I need. And then I can use the molar mass of sodium carbonate to tell me the number of grams. So hopefully that worked through solution made sense. And again, that's the first quantitative piece we're going to deal with here. The next piece that we're going to get into is working through one problem that's a fairly large problem. So I'm going to flip back here just for a second to highlight this sort of experiment that we talked about. Imagine taking a buffer here and then adding a fixed amount of either acid or base and seeing how the pH is going to change. That's essentially what we're doing with this next problem here. We're first going to figure out what the pH of that solution is. Oops, this is the problem we just did here. We're first going to figure out what the pH of this solution is. So again, we're going to have a certain buffer that we're going to figure out the pH of. And then we're going to add a strong acid to it. And we're going to ask what happens to the pH. And then we're also going to say, let's imagine we take that same buffered solution and instead of adding an acid, we add a base. What's that pH? So what we're going to have here is essentially two kinds of calculations that we need to do. The first thing we need to do is what we're going to refer to as a chemistry calculation. We're going to do an ICF table. Remember, anytime you see an arrow like this, that tells us that it's an ICF table. So we're basically doing some chemistry in a neutralization reaction like we know happens with buffers. The addition of base is going to react with our acid soldiers, neutralizing that added base, and then leaving behind more of the conjugate base and less of the weak acid. The flip is true when we do the neutralization chemistry with the addition of a strong acid to a buffer. That strong acid is going to react with our conjugate base. This is going to generate more of the weak acid, but neutralize that addition of that strong acid. So the first part of our calculations are going to involve recalculating the amounts of weak acid and conjugate base that we have. Now, once we have these new amounts, we need to use either an ice table or the Henderson-Hasselbalch equation, and I'm going to show you both to go through and calculate pH. So because these problems are new, I am going to tell you what the answer is at the beginning, and if you wanted to try to work through it on your own. But because they're kind of a new and intense and challenging problem, feel free to sort of let this play through. Pause it if you want to be able to write down the answer, but to let it play through so you can see how it's worked out. So the problem-solving strategy that we are going to employ throughout the entirety of this chapter is sort of a four-step process. The first thing that we're going to do is we're going to say, who's there? Who's in solution? Who are the important species that we need to think about? We employed this strategy when we first learned about adding salts to solution in chapter 18. We looked at everybody that was in solution, and then we said, who can do chemistry? So again, thinking about who can do chemistry, let's identify what's actually happening with that chemistry. Write down the chemical reactions that we have and the important chemical equilibria that are going to be able to affect pH. We're going to use two kinds of tables in these kinds of problems. When we do reactions, we're going to use ICF tables to keep track of what's going on. And when we have chemical equilibria that are left, we're going to do ice tables to be able to kind of reconcile the equilibria and the pH at the end. Again, we're going to have Ka and or Kb values that we'll need to think about in order to do our ice tables or think about using the Henderson-Hasselbalch equations. So again, a unique problem-solving strategy. We're going to use that same strategy as we work through all of these problems. Okay, so here's our big problem. We're actually only going to work through parts A and B together here. I encourage you to try doing part C on your own. I've got the answers provided here for what you should get for all three parts. Now, hopefully part A is pretty straightforward. This is very similar to a kind of question that you'd see in chapter 18. Basically, if we were to have a salt solution, for example, we might have some weak acid. And again, here's a salt, which provides the conjugate base. So this is kind of like a problem we'd see in chapter 18. Then we're going to say what happens to that solution if we were to add 0.02 moles of sodium hydroxide. So this represents kind of a new calculation, new chemistry that we've seen. We're sort of thinking about adding this all at once, so there's no volume changes we need to think about. You've done stuff with titrations in lab, and we're going to get to titrations in our next lecture, but this one really is all about just adding this chemical to solution and not really thinking about it doing anything to change the volume. We're just going to be using 0.02 moles, in this case, of strong base in B or strong acid in C. So what we can see here is we have a starting pH of 4.74 with our buffer. If we add in some strong base, we see a slight increase. If we add in some strong acid, we see a decrease. So let's work through part A here. And again, if you want to take a stab at trying these on your own, go ahead and pause the video. If you want to kind of watch through the worked out solution, feel free to just let it play. Okay, so if we think about this first part, haven't done any chemistry, we just have a buffered solution. So thinking about writing the species, who's in solution? Well, we've got an acetic acid solution that they said is 0.5 molar, and we've got a sodium acetate solution that's 0.5 molar. So even though we've got sodium that's there at 0.5 molar, that's a spectator ion. Remember that from chapter 18? We don't see any acid-base or pH changing chemistry with sodium ions. So it's a spectator ion. So this is what we have in solution that's relevant to affecting the pH. Because we haven't added anything to our buffer, there's no chemistry that we have to think about. For the problems that we're going to work through in this section, there's no changes in volume because we're just, even in our next problem, when we add something, we're not changing the volume. So we're going to treat this problem just like we've treated all of our problems previously. Start with a balanced chemical equation. This is what we can have happen when we have these species in solution. We've got a weak acid that can dissociate into its conjugate base and H3O+. Because this is an acid equilibrium, we're going to want to be using a Ka value. Now let me highlight, you could have just as easily written this reaction in the opposite direction. That would have been totally fine, but you would then have to use a Kb value. Okay? ICE tables that contain molarities. Now this is the one piece that's different from what we did in chapter 18. In chapter 18, you might have only seen a problem that said, what's the pH of a 0.5 molar acetic acid solution? Or a 0.5 molar sodium acetate solution, not a solution that contained both of them. So this is a piece that's new, and don't get tripped up by this. Don't put a 0 in here because it's not 0. They tell us that we start by having that amount of both of these chemicals, 0.5 molar, weak acid, and conjugate base. Now again, this is where it might get a little bit confusing whether you put plus x's or minus x's, but as we're going to see on our next slide here, because we make an assumption that x is small and the x's are going to go away, it doesn't matter whether it's plus x or minus x here. So don't worry and stress about that, because for this ICE table, it's not going to matter because we make an assumption that x is small. Propagate your values here in your ICE table to get 0.5 minus x, 0.5 plus x, and x. So I'll give you a minute to kind of let this sink in and think now again about what this means. How would we solve this ICE table to essentially get our x, because that's going to determine what H3O plus is. So moving on to solve for x, we're going to treat this like we did all of our other problems where we were solving for x. We're going to have an equilibrium expression. Because we wrote an acid equilibrium, we need to make sure we use a Ka value. We still want to make sure that we're thinking about the same principles that we talked about in chapter 18 when we think about doing an assumption. So you can either do a pre-check or a post-check to make sure that we're okay making our assumptions. but putting in those values that we have, we're going to have a 0.5 plus x on top and then a 0.5 minus x on the bottom. And again, seeing that we make this assumption here, it's not going to matter whether it was a plus or a minus x because we're assuming our x's are small and they go away here. So again, don't worry about that. But we're going to see that because these values are the same, they actually cancel. So our x in this case is going to be equal to the Ka value. Take the negative log of that x, right? And that's going to be equal to our pH. See if this makes sense. This is also our Ka value. So taking the negative log of it is our pKa value. So remember when we talked about the concentrations of weak acid and its conjugate base being equal? We said that pH would be equal to pKa. So we can see that play out here if we solve this with an ice table. And I want to encourage you to still use ice tables if that's what's most familiar to you. But I want to show you how simple this calculation can be. If we know we've got a buffer solution, we can use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation will give us pH when we put in the pKa value, which again is just the negative log of Ka, plus the log of what our conjugate base concentration is, plus our weak acid concentration. Those were these values right here. Because these were equal, we're going to have the log of 1. The log of 1 is 0. So again, here we see that pH is equal to pKa. That's what we, in essence, got to the same answer going through an ice table. So again, I wanted to show you that you can solve this problem using chemistry that you already know, which is an ice table, and then solving for x. But importantly, you can very simply use a new equation anytime you know you have a buffer. And you have to have a buffer. You have to have a weak acid and its conjugate base. You can use the Henderson-Hasselbalch equation and just put those two values in, put the pKa value in, and solve for your unknown. Very simple to get pH when you know you have a buffer solution. Okay, moving on to the last little piece here. Let's imagine that we are going to add some base to this. Okay, so we're going to add 0.02 moles of sodium hydroxide to this. We're going to assume that there's no change in volume, so we're still going to have 1 liter of solution. This is something that's going to change. This is going to be an important player when we get to titrations in our next lecture. But if you want, take a stab at working through that problem. Again, highlighting, we know that the pH is going to increase a little bit. See if you can do the chemistry that gets you to 4.78. So start by writing who's there, identifying the chemistry that can happen, keeping track of it with an ICF table. We just said there's not going to be anything to consider with volume changes. But then once the chips have fallen, once the chemistry has happened, look at what you have left, and then you can either do an ice table or again the Henderson-Hasselbalch equation to figure out pH. In my worked out solution, I'll actually show you both again. So pause the video here if you'd like to try this on your own, or let it play if you want to see the worked out solution. All right, so thinking about who's there. We still, again, have our weak acid and our conjugate base, remembering that that sodium is not going to have any impact here. It's a spectator ion. We've got 0.5 molar each. We've got a liter of each. The new piece is that we've added 0.2 moles of sodium hydroxide. Again, sodium, from that sodium hydroxide being a spectator ion, the only player is that hydroxide that we've added. So we've added 0.2 moles of this. If we know how many moles of our weak acid that we have, we can tell how much of that soldier is going to be depleted, how much of that army is going to be depleted by the amount of hydroxide that we add. So we need to convert the use the molarities in the volume here to figure out how many moles of acetic acid we have. This really represents the size of our army. We've got 0.5 moles of our weak acid army, and we're adding 0.02 moles of a strong base. So that's going to deplete this by a little bit. Not completely, but just a little bit. And we can use an ICF table to determine how much. So pause the video here if you want to try working through the ICF table on your own, or let it play if you want to see it worked out. So here's our ICF table. Just another little review here. When you have an ICF table is going to be used when you have chemistry that looks like this. One-way reactions, not equilibria. We need to have moles in our ICF table, not molarity. And we don't ever see variables in this part of our chemistry here. We're just using an ICF table as a way to keep track of everything that's going on. So we write the things the same way in that we start with a balanced chemical equation, but not for an equilibrium, for the chemistry that's going on. The chemistry that's going on is our weak acid army is going to sacrifice itself for the base that's added. We're going to generate some of our conjugate base army, neutralizing the hydroxide to generate water. Keeping in mind that there has to be moles that are in this table, we know that we've got 0.5 moles of our weak acid army, and we're adding 0.02 moles of our hydroxide army. This becomes our limiting reagent. We're going to use all of it up. So because we know the amount that gets used up here, that determines the amount that gets used up of our weak acid army. So we're left with 0.48 moles of our weak acid army. We've neutralized all of our hydroxide, and importantly, we've added 0.02 moles to our conjugate base army. Now, this chemistry became a little bit easier, or these calculations, I should say, became easier because we have 1 liter of solution. The number of moles that we have works out to be the molarity of that solution after all the chemistry has happened, after all the chips have fallen. This is what has happened. Our weak acid army's concentration has gone down, our conjugate base army has gone up, and we have neutralized that hydroxide invader. So now that we know the new concentrations of our species, pretend like this is a part A problem. Figure out what the pH of the solution is now that these are different from 0.5 and 0.5. So pause the video if you want to try that on your own, or let it play if you want to see the worked out solution. So again, we can treat this and solve this via an ICE table. So again, we've got our new concentrations of weak acid and conjugate base. So using the equilibrium that we'd think about that would exist between these, we can start by writing our balanced chemical equation there for our equilibrium reaction. Because we have an equilibrium that we have there, we're going to have an ICE table. So here's our ICE table. Again, our ICE table here is going to have these new values here. Not 0.5, but 0.48. Not 0.5, but 0.52. Treat this the same with our minus x's and our plus x's. And again, it really doesn't matter whether they're minus or pluses because we're going to do these assumptions that allow them to go away. But what I want to highlight is the only part that this becomes different from what we had in problem A is rather than these being 0.5 and 0.5, our weak base army is a little bit bigger, our weak acid army is a little bit smaller. Calculations become exactly the same to go through and solve for X. X again gives us our H3O plus concentration. Negative log of that gives us pH, which is a little bit elevated because we added hydroxide to our solution. So again, you can solve this problem using an ICE table, but you can also solve the problem, and I don't have it shown here, doing a Henderson-Hasselbalch equation. You could put in that the concentration of your conjugate base is 0.52, the concentration of your weak acid is 0.48, and you will still get the same answer of 4.78. So what I want you guys to try on your own is going through the same calculations, but seeing how they'll be different if we now add 0.02 moles of HCl. I'd encourage and direct you to go to the Blackboard site to see the worked out solution for this problem. And again, you're going to get that the final answer will be 4.72. So again, if you want to see a worked out solution for that, you can watch the video online on Blackboard. It's not done with an iPad here. It's actually done sort of with an old school mechanism with how I used to do online videos, where I literally have my camera that's positioned over a paper that I'm actually working through the solution on. All right, so lots of things that have sort of come together with that problem. And so that represents the end of this material for our first lecture here. And I apologize, I know this video was probably a little bit longer than I had intended it to be, but I wanted to make sure to go through this slowly and thoroughly enough to make sure that you guys understood these qualitative aspects of buffers, how we make them by, having a conjugate acid-base pair, how we think about making the best buffer, thinking about capacity and range. And then again, we did a pretty involved problem thinking about how we calculate pH of buffer solutions. And again, some qualitative stuff, thinking about pH, pKa, protonation state, and then again, this all-important Henderson-Hasselbalch equation. Not an equation that you're going to need to memorize. It will be provided for you on the front of your exam, but you do want to know how and when you can use it. You only can use it if you have a buffer.